Alright, so in this video we're going to be looking at the oxymercuration demercuration reduction reaction. It's a mouthful, but we'll just call it oxymercuration. So oxymercuration is another way that we can add a hydroxyl group to an alkene. We've seen that we can use acid-catalyzed hydration, and that's one way we can add a hydroxyl group, and oxymercuration is another way. But there is an important distinction to make, and this distinction is going to especially be important when you're looking at different synthesis reactions because you want specific products to form. So there are actually three main ways that you can add a hydroxyl group that you're going to need to know. We've already looked at acid-catalyzed hydration, and in this video we'll look at oxymercuration. And in a later video we can look at that third way. But before we move any further, let's just look directly at what it is we're accomplishing with oxymercuration. We will go into depth about the actual reaction mechanism with the arrow pushing and everything, but that'll be later on in this video. Again, in case you're short on time, you just need to quickly see what is the product that we would form using the reagents in oxymercuration. And also just because most professors don't actually require you to know the entire reaction mechanism, especially on an exam, you aren't going to be expected in most Orgo 1 classes to draw out the full mechanism for oxymercuration. But in case you want to know it, because you're curious, it might help you better understand, or maybe your professor does want you to know, that will be covered later in the video. But we'll just start by looking at exactly what we're starting with, the different reagents we use, and what our product is. But first, let's start off by looking at a quick review of what it is we've seen before, which is acid-catalyzed hydration, which is an important way. It's one of those three ways that we need to know to add that we can add a hydroxyl group. So let's say we're starting with this alkene here. So if we have an alkene that looks something like this, and we want to do acid-catalyzed hydration, for example, then we can just write that simply as H2O/H3O plus. This is referring to our acid-catalyzed hydration reaction. And we would see that the product that we'd form is going to be this kind of slide. The product that we form would look something like this, right? We have our methyl group here, and the OH is actually going to be on this carbon. Now, you can see that the the OH group is actually attaching to a carbon that is not even involved in the double bond, and that's because you'd see that the intermediate that forms, right, is one that has a secondary carbocation. And you'll notice that whenever we're doing a reaction like this, or any other reaction when we're forming a carbocation, it's important to be aware of the carbons that are near it. Well, this carbon is primary, but this one is tertiary. So if we were able to form a tertiary carbocation as opposed to the secondary one that we do form, that would be a lot more favorable, a lot more stable. So what you'll see is that we'll actually undergo a hydride shift. Remember, there's an invisible hydrogen on this carbon, and so we will undergo a hydride shift where a hydride is a hydrogen with two electrons, right, with a lone pair. So this hydrogen with both electrons involved in this bond will shift to the carbocation, forming an intermediate that has a tertiary carbocation instead. So it's because of that that we'll end up forming this OH group, or we'll end up forming a product where the hydroxyl group is attached to this carbon here. So that's actually an important realization to have, is that when we're doing acid-catalyzed hydration, we can have carbocation rearrangements, we can have hydride shifts, we can have methyl shifts. But when we're looking at oxymercuration, that is not going to be possible. We'll see why again when we look at more depth in the mechanism itself, but for now, just know that if you want to undergo a reaction where we can't do any where we want to attach a hydroxyl group and we can't do any carbocation rearrangements, right, then we would want to do oxymercuration. So if we want to do the same starting material, if we want to use the same alkene here and form a product that looks something like this, right, where our OH is on this carbon, we can't do acid-catalyzed hydration because a hydride shift would happen, and so we would end up forming this product. So if we wanted to form a product that has the hydroxyl group on the secondary carbon, we would have to do oxymercuration. So again, for now, just look at what reagents we will be using. Again, in case you're short on time, you need to quickly memorize this for a quiz or an exam. Just knowing we're using this mercury acetate in water. That's the first step. And then we will react with NaBH4. So we'll see why everything is reacting with what in the mechanism. But for now, if you just have to memorize something, memorize the reagents that we'll be using. So know that we won't be able to do any carbocation rearrangements. So if you want to ensure the formation of just this Markovnikov product, nothing where, just the Markovnikov product, the major product involving only the carbons in a double bond, then you would use this oxymercuration. There is another, again, the third, this is the first one, it's the second one, and there is a third way to add a hydroxyl group, and that's going to be with hydroboration, where we're reacting with BH3, and that will be in another video. But in that type of reaction, we would end up forming a product where the hydroxyl group is actually attached to the least substituted carbon. This is going to be ensuring the formation of the anti-Markovnikov product, which is very interesting, right? Because we always see the Markovnikov product being formed. But if you want to create a product where the OH group is added to the least substituted carbon, where you want to ensure the formation of that anti-Markovnikov product, you're going to have to use hydroboration. But like I said, we will look at that in another video. And so for now, let's quickly look through the reaction mechanism for oxymercuration. All right, so let's look at a simple starting compound here, or a starting, alkene that we can react in this oxymercuration mechanism. So if we're starting off with something that looks like this, right? We know that in oxymercuration, we're reacting with this mercury acetate, which we saw earlier. So we're going to have Hg, which is our mercury, attached to two acetates here, right? So what will end up happening here is these nucleophilic electrons in the pi bond are going to go on and attack the electrophile, which is our mercury here. And know that mercury cannot form 3 bonds. So when we have this happening, one of these acetate groups is going to have to break off. So we have these electrons in this bond go on as a lone pair and kick off this OAC. So when we see this happening, what we're left with is just the acetate floating in solution, and also we're now left with the dilemma of figuring out where is the carbocation going to form, right? Are we going to end up forming a primary carbocation or a secondary carbocation? Well, we know oxymercuration is a reaction that goes by Markovnikov's rule, right? We're going to want to form the product that is directly formed from the more stable intermediate. So we know that we want to form a secondary carbocation. So if the carbocation has to form over here, then that must mean that this HgOAC must attach to this carbon. So we get an HgOAC attached here and a carbocation here. Hopefully that makes sense, right? If we wanted to form a primary carbocation, then, because remember, if we were to have the this HgOAC attached to this carbon, then the carbocation would form on the primary carbon, which would be much more unstable. So in order to allow for the formation of an intermediate that is more stable as per Markovnikov's rule, we have to have the HgOAC attached to this primary carbon here. So what we see, though, is you may think that now that we've formed a secondary carbocation, which is adjacent to this tertiary carbon here, we're going to want to have a hydride shift, this carbocation rearrangement. But what's going to actually happen is, before that can happen, this mercury here, which has a lone pair, is going to go and attack the carbocation. And that happens essentially immediately as the carbocation forms. So this attack by this lone pair on the mercury is going to happen so fast that it's going to, again, occur before any sort of rearrangement, so any sort of hydride shift can occur. And so what's going to end up happening then is we'll form an intermediate that looks something like this, where we have, again, that HgOAC OAC here, but we have the mercury here not only attached to this carbon, but also bonded in this way. So know that this first bond here, the electrons that are making this bond, are going to be the electrons that made up the pi bond here. So these are these electrons, right? Whereas the bond that's forming here is occurring from the lone pair that was on the mercury. So let me draw this a bit better. Right, hopefully that looks better. I can also just redraw it once here just to make it look a bit nicer, right? We can have our HGOAC, where our mercury is bonded to both carbons, something that looks something like this. All right. So it's actually at this point that things start looking a bit more complicated. So it's important, I actually forgot to note this down here, but that this mercury now has a plus charge here, right? So this is a mercurinium intermediate. But what's important to understand is despite this mercury having this positive charge, it still draws on these electrons here, right? It's pulling on the electrons in this bond. And so because of that, each of these carbons is going to have a partial positive charge because they're losing some affinity for these electrons in the bond to the mercury. But this partial positive charge is not going to be equal amongst both of these carbons, right? We know that the secondary carbon here has a much it's going to be much more stable, or it's much more capable of holding on to a positive charge. So the partial positive on this carbon is going to be greater than the partial positive on this primary carbon. Both of them are partial positives, but this magnitude of positive charge is still greater on the secondary carbon. So this is going to be, I'm going to try to draw it a bit smaller. This is a partial positive, and this is a slightly greater partial positive. If you can see that I tried to draw that sign a bit larger. So what's then going to happen is when we have a water molecule that comes in, because this carbon is more partially positive than the other one, we're going to have the lone pair from the oxygen attack this carbon as opposed to this one. So what will end up happening then is, if I erase this, so what we'll see is that, well, now firstly, the bonds or the electrons in this bond must now go and collapse back onto the mercury because the carbon can't have, another bond here, right? So you must have these electrons go and collapse, and so we'll form another intermediate here. So if I can just get rid of this, you'll see the intermediate that we now form will look something like this, where we have the HGOAC on this carbon, and now a hydroxyl group on this carbon. That was actually not a hydroxyl group just yet, right? I forgot. We have to technically draw it out like this, right? We haven't shown how we lose the second hydrogen yet, so that's another part of the mechanism. So we end up with an intermediate that looks something like this. All right, so what you need to remember is that this oxygen does still have a single lone pair. And so what will happen is we have another water molecule in solution that will approach. It'll go on to attack a hydrogen, which then puts these electrons back on the oxygen as another lone pair, giving us the next intermediate. I know there's a lot of them, looking something like this, right? Where we have just an OH, and now the oxygen again has two more lone pairs, and there is no charge on this group anymore. It's back to neutral. So kind of getting rid of this, hopefully you noted it down, what we'll see is what we have now is going to be very close to our final product, right? We have an OH on a Markovnikov alcohol, right? But we just still have this HGOAC on this primary carbon. And this next step is, there is no real mechanism to know here when we have the sodium borohydride reacting. Many professors, or really all professors, don't require you to know any real mechanism, just know what the product of this is. And so this is effectively a reduction step, and we call it a reduction just because we're attaching a hydride here, right? So just know There is no arrow mechanism you need to know for this part. Just know that the HgOAc is going to be replaced by a hydrogen from the sodium borohydride, which is going to give us the final product, where we have this alcohol, and remember there's an H here. But just know, again, because this is a skeletal structure or a line structure, we don't tend to include these hydrogens. They tend to be invisible. So this is going to give us that final product that we talked about at the start of the video. So hopefully that made some sense. I know it's a bit of a longer mechanism, a more complicated mechanism than what we've encountered so far. So be sure to go and watch back if you think you need to do that. And again, this is just the second way that we looked at how we can attach a hydroxyl group to an alkene. Be sure to look out for the next video on hydroboration, which is going to be that third and final way that we're looking at in Orgo 1 to attach hydroxyl groups. And yeah, so if this video is helpful, please show your support by liking and subscribing. Leave any questions you may have in the comments and suggestions for future videos as well. And I will see you in the next one.